Welcome back, geologists and mineral lovers. Today we are diving into the world of oxides, one of the most important minerals and intriguing minerals on Earth. Please stay tuned. Don't forget to like, share, comment, and hit the notification button below so that you get notified once we upload new content. Stay tuned. So, basically, oxides compounds which composed of the oxygen, which is bonding with other metals or other elements. Okay, so they are basically classified based on their oxidation state, the oxidation state of the oxygen atom and the other elements present. Okay, and they basically occur as accessory minerals in both igneous and metamorphic rocks, and then they occur in sedimentary rocks as resistant detrital grains. That is to say, the grains which they are resistant to weathering. All right. And then oxides minerals are relatively hard, dense, and refractory, meaning they withstand high temperatures, and they are very dense minerals such as the uraninite because of the uranium content, for example, and they are relatively hard. For example, when we're looking at the mineral corundum. Okay. Bond type in oxides is generally ionic, meaning there's some what you call the ionic bonding. We're not going to be focusing on the covalent bonding, but ionic bonding, and they are grouped into simple oxides and the multiple oxides. All right, simple oxides. The basically we have got one metal and oxygen, and then multiple oxides would have more than two elements, and together with the oxygens. Okay, so when we're going to, in terms of the multiple oxides, we're going to be looking at the minerals such as the magnetite, the magnetite, for example. It's one of the minerals which are classified as the multiple oxides. And then simple oxides, we're going to be looking at the hematite, and the corundum, and many others. All right, so simple oxides, we've got cuprite, periclase, hematite, and the rutile, and we've got the rutile group and the hematite group. So in the hematite group, we're basically going to be looking at the corundum, the hematite, and the ilmenite, and then in the rutile group, we're going to be looking at the rutile itself, the pyrolusite, cassiterite, and the uraninite. So basically today, we're going to be looking at all these minerals. We're going to be looking at their physical properties and their distinctive feature. How can we identify them when we are in the lab? Because these are one of the most intriguing minerals on Earth. So the multiple oxides, we're going to be looking at the specifically today, going to be looking at spinel, magnetite, and the chromite. All right. So these are the most important minerals to be worth understood. All right. Although we also have got the zinc aluminum oxide, which we call it garnite. Just know it's there, but we're not gonna look at its physical properties into detail. But we're basically gonna be looking at the spinel, magnetite, and the chromite. So what do we get from these oxides? So where what the element iron, we get it from the minerals hematite, magnetite, and the goethite. All right. We get that from we get iron from these three minerals. All right. For example, when we're looking at the magnetite in the bushveld complex, especially in the upper zone of the bushveld complex, that's where we get this iron in South Africa. Okay. And also the chromium. Chromium, we get it from the mineral chromite, and also in the bushveld is prominent. And then also the manganese in the Transvaal supergroup in South Africa. We get the manganese from what you call pyrolusite, and the tin from cassiterite, and the uranium, which is the radioactive element. We get it from the uraninite. Uranium, we know it's very heavy, making uraninite become heavy. Now, why these oxides are very important? Uranium from the uraninite, it's good for the nuclear fuel production, whereas tin can alloy with what you call the other metals to form what you call the bronze. Okay, for example, if we The bronze we know it's a mixture of tin and copper. If we combine or if we alloy tin and copper, we're gonna form a bronze. So which this is very important to be used as sculptures, as tools and weapons. Okay, a tin, for example, is also used in soldering in soldering alloys where it forms a low a melting point alloy with metals like lead, silver, making it suitable for joining electronics. And then manganese, on the other hand, is good for it's good in steel making, whereas chromite is good for stainless steel production. So the distinctive feature of the multiple oxides, with the multiple oxides like magnetite, spinel, and chromatite, and chromite, that is to say, we know in terms of magnetism, magnetite will be the only thing which has got a strong magnetism, whereas the chromite and spinel, they will be weakly magnetized, or they might be non-magnetic. Okay. Then in terms of color, magnetite is black. Okay, in color is black and also having what you call a black streak, whereas chromite and spinel, chromite will be brownish black. Spinel can vary in color. It can be red, green, blue, black, okay, with a white streak. And then magnetite might partially react with the hydrochloric acid, whereas the chromite, it will be highly resistant to the acid attack. So, like I've mentioned, that the chromite, it will be brownish black. That is its distinctive feature. It will be brownish black, and then it will be weakly magnetic. But now it has got this metallic luster, or submetallic to metallic luster. That is the chromite. And then the streak, it will be brown. That is to say, if you were to scrap this on the polysilicon, it will show this brownish streak, and then because of it is brownish to black in color. Okay. Then we also have got the magnetite is strongly magnetic. That is its distinctive feature, is strongly magnetic. That is to say, strongly magnetized, and it has a black streak. It has a black streak. It has a black streak, and it's black in color. Okay, so that is the distinctive feature of the magnetite. It's highly magnetic, and it's black in color, and it has got a high streak. And then spinel, on the other hand, it has got pyramids, which they are double. You've got the other pyramid at the top and the other pyramid at the bottom. There is the pyramid at the top and the pyramid at the bottom. All right, and that is why we're saying two back to back pyramids. That is to say, the other one at the top, the other one at the bottom, and it has got this vitreous to dull in luster, and then the color it's variable. You can have for example, this it's black, and we're gonna have a red one, a pinkish one. We're gonna have a red one, orange or blue, green. All right, that is to say, the colors will be variable. Now, it will be non-magnetic. It will be non-magnetic when compared to other multiple oxides, for example, magnetite. So, like I mentioned before, that spinel and the chromite, they will be weakly magnetic, and whereas the magnetite, it will be highly magnetic. Then we've got the simple sulfides. The simple sulfides, they are distinguished by, for example, hardness. We know corundum is the hardest one with the most scale of 9. It means corundum, it can scratch almost all minerals. For example, if you want to test the corundum, you scratch the quartz with this corundum, and it will easily scratch quartz. So it means the only thing that it will be unable to scratch, it will be the diamond, okay? Because the diamond has got more scale of 10. And then hematite and ilmenite, they are moderately hard, whereas cuprite and pyrolusite, they are very soft. It means a special pyrolusite, you can scratch it with your fingernail. And then hematite and cuprite, because of the reddish color, they are reddish in color, and that's why they would leave the reddish to brown streak. They will leave reddish to brown streak. And then pyrolusite, it will be black streak. And then cassiterite, rutile, and corundum, they will have white streak. That is to say, when we are generalizing all these simple oxides. And then in terms of magnetism, hematite and ilmenite, they are weakly magnetic. Uranite is radioactive because of uranium, and then cassiterite, rutile, and uraninite have got high densities because of the presence of uranium, for example, in the uraninite. Hematite, the distinctive feature of hematite is the reddish brown streak. It doesn't matter as to whether we're looking at this earthy hematite. We've got the earthy hematite and we've got metallic hematite. So the metallic hematite or earthy hematite, they will all leave the reddish brown streak. That is the distinctive feature of this hematite. And then it will be, don't rely too much on the magnetism because it is weakly magnetic. And the ilmenite, it looks like magnetite. It looks like magnetite, but this one it will be less magnetic, but it looks like hematite, not hematite, but magnetite. Okay. Corundum, the distinctive feature is this shape, hexagonal shape, 1, 2, 3, 4, 5, 6. It has got hexagonal shape, but now the distinctive feature again, beside this hexagonal shape, it will be hardness. It means it can scratch all other minerals. It can scratch all other minerals. But like for example, you can scratch quartz, but now obviously it is heavier. Now it's hard, but cannot be harder than the diamond. Okay. Now we've got the impure one, which is colorless, and then because of the presence of impurities, we can have colorful ones. Okay, we can have colorful ones. And then pyrolusite, like I said, it's easily to be, scratched because it's softer. And then it leaves, it's like what you call the, what's this mineral for pencils, for making pencils? Graphite, yes. It leaves powder, like what graphite can leave, okay? It's like a pencil, all right? And then usually if you want to know that you're dealing with pyrolusite, what do? You react that with hydrochloric acid, and then it will strongly react with hydrochloric acid. And then the distinctive feature, it will be this fibrous crystal habit. It will be this fibrous crystal habit, and it is metallic to dull in luster, and sometimes we can have a black one, and then sometimes we can have this dark gray kind of vibe. And then rutile, rutile is typically reddish brown or golden. Okay, its streak is pale brown to light yellow, which helps distinguish from like hematite. All right, crystal habit, it forms nettle-like or prismatic crystals. Okay, we've got nettle-like prismatic crystals. Sometimes it can be stubby. Okay, it's short. All right. And then it has a brilliant metallic to adamantine or diamond-like luster, making stand out under hand lens or microscope. And has got high specific gravity, meaning it feels unusually heavy for its size. Okay. But now it can scratch glass, but it's softer than quartz. Okay, it's softer than quartz. And then cuprite, more or less, it's also reddish, but it can have a greenish tint. It can have a greenish tint. Still remains reddish brown because of that is the distinctive feature, reddish brown. All right, so the streak, it will be reddish brown. That's when you'll be knowing that I'm dealing with the cuprite. Okay. And then also you can have this green tint when exposed obviously to on the air. Okay. Due to what? Secondary copper and mineral alteration. All right, if you haven't yet visited the video on the for example, on sulfides, you'll agree with me that bonite, for example, bonite and the chalcopyrite, they also have got this tint because of the effect of the oxidation. Okay. Luster, it's adamantine to submetallic. It's more or less the same with that of the rutile. It has got this adamantine or diamond-like. And then association reaction often found with malachite, chrysocolla, and the azurite. Okay, azurite in oxidized copper deposit, and then it weakly react with the hydrochloric acid, unlike the malachite with which effervescence strongly. Periclase is usually colorless. Okay, it's usually colorless, white or gray. You can see it's usually colorless, but because of some impurities, you can have you can be greenish or brownish tint because of the presence of some impurities. But now streak, it will be white. The streak, it will be white. Periclase, it exhibits vitreous or sub-vitreous luster. You see down, it's like glassy kind of vibe. That's why it's vitreous. And you can sometimes it can be transparent to translucent, meaning sometimes you can see through, but sometimes you can see just inside but not through. That's why translucent. Okay. And then obviously something that it has got the glassy luster, we know it will break, it will fracture, usually conchoidally. So periclase, it will also have the conchoidal fracture. And then cassiterite, the cassiterite, it is you can have the black one, you can have a black one, you can have a brownish or reddish brown or black one. All right, streak, it will be white to light brown. Okay, and then crystal habit, it's usually twinned. It is usually twinned. Can you see? It is usually twinned. It is usually twinned. But because we know from the cassiterite, what do we get? We get the tin. Okay, and then it's highly resistant to acid and weathering, and that's why it's found in placer deposit. Which is why in the beginning when I mentioned that these oxides, you usually find them in igneous and metamorphic rocks, but the resistant ones, for example, this cassiterite, you find them in associated with sedimentary rocks. So that is the distinctive feature of this cassiterite. Cassiterite is highly resistant, and then it's also adamantine in luster. And then it's usually twinned and it's prismatic. Usually twinned and prismatic. Usually that is the distinctive feature: twinned and prismatic. And then last but not least, uraninite. That's where we get the uranium from. Usually it has got this metallic luster. Okay. Or sometimes it can be submetallic and then to greasy, a submetallic to greasy. Sometimes with a peachy or dull appearance. Okay, for example, here it has got this dull appearance. All right, that's got this dull appearance, and then in terms of color, you can have brown to black to brownish black. Okay, sometimes with metallic or dull appearance. Can you see? Here's metallic. Here is dull appearance. Okay, but it's highly radioactive. It means if you have Giga counter, you can detect this uranium, because uranium is highly radioactive. So basically that is quick look into the oxides. I hope these physical properties and what oxides are, they will help you to identify these oxides in the lab, because these oxides, they are obviously also important like other minerals. So these are very important to be understood as well. So thank you guys for joining us today. This was a quick look into the oxides, and I'm really thankful for joining us today, guys. And if you haven't yet subscribed to our YouTube channel, you are more than welcome to subscribe to MJ School of Mining and Geology. I would always like to say we're really thankful, and until next time, cheers.